Perhaps one of the most important skills you need to develop as a programmer is the ability to identify what constitutes a good function, and in particular, how should you decompose your code into separate functions, especially when should you take a long function and split portions of it off into separate functions. Well, the three most important guidelines are that a good function does what the name says it does, and only that one thing, is generally shorter rather than longer, and it doesn't have too many parameters. In your whole code base, you generally want your functions to on average have somewhere like 1 to 3. That's the average though, so you can have some functions where the number of parameters is like 6 or 7, though that's generally the high end. Once you get up beyond 6 and 7 parameters for a single function, that's generally unwieldy. If you find yourself with such a function that seems to require too many parameters, the solution there is either that your function isn't really doing just one thing, that you're bringing in all this input data because the function is taking on too much responsibility, or the problem is that the parameters are really things that should be bundled together in a single object, either in some collection object like a list or map, or in some declared type that should exist in your code, some class you should have created. It's either one of those things, or both. It could be that you need to split the function up into more than one function because it's taking on too much responsibility, and it could also be the case at the same time that some of those parameters need to get bundled together into a single object. Now, as for the length of your functions and methods, there's no definitive answer for how long they should be on average. Some people will tell you that an average length of 40 lines is the ideal, other people will tell you it's 10. Most people, though, myself included, will tell you it's somewhere around 20 to 30 lines. That's the ideal length for most functions. Now, notice I said average function and most functions. It's perfectly okay in your code to have a percentage of exceptions, some which are quite long, up to like 100 or even 200 lines in length, and other functions which are really short as a single line or two. The most important criteria for appropriate length is, again, does the function really do the one thing that the name implies it does? If you find that you have snuck in extra functionality and responsibilities to a function, generally you want to take those chunks of work and split them off into their own functions. Or perhaps say you have a long function where there are sections which do still fall under the banner of what the name of the function implies that function does, and yet you have this whole chunk that comprises a discernible subtask, something which is a step along the way to accomplishing that larger goal. Well, when you have a significant chunk of code like that within a function, it generally makes sense to split those chunks off into their own functions. For me, the rule of thumb is if I were to take these 5, 10, 15 lines of code and split them off into their own function, do I know what I would call that function? And if there's an obvious name for that function, then the answer is a strong yes. So usually a function which seems overly long, that's just a symptom of a deeper problem where the function isn't really doing just one thing, or it contains code that accomplishes some subtask which itself could be split off into a separate function. If you just keep a lookout for such cases, over time most of your code will decompose into functions which on average are reasonable length, something like 20 lines. On the other end of the spectrum, you generally shouldn't hesitate to create functions which might seem overly short, such as just one or a few lines. Those actually can be very useful. I think most programmers would agree that you wouldn't want all of your functions to be 2 or 3 lines in length, because even though then all your functions individually would be easy to understand, the whole of your program would likely be harder to understand. To locate pieces of functionality in the code, you'd have to identify dozens of functions to find just one piece of functionality, rather than looking at just 1 or 2 functions. So I believe that's why most programmers prefer an average length of something more like 20. On the other hand, a very short function can be useful in a case where, say, you have some expression which you find is repeated throughout your code. Rather than having that same expression repeated many times, it's better to encapsulate it in a function, even if that function is really short, even just a single line that does 1 or 2 math operations. It may seem silly to have such a short function, but if that particular operation has been repeated in many places, the situation you don't want to be in is finding out that, oh wait, I need to change that operation everywhere it occurs, and so I'm going to have to go through the code and change it in every single place. If instead of using that expression repeatedly, you encapsulated that into a function and then just invoke that function wherever the expression was meant to occur, you would only have to change this code in one place where the function is defined. So you really shouldn't hesitate from creating a function just because you think it's too short. If it's an identifiable operation which you use repeatedly in code, make that a function. So, if you follow these general guidelines, you should write some pretty decent functions. The best possible functions, though, the ideal functions, they conform to the stricter, more mathematical sense of a function, which is that they are idempotent. An idempotent function does precisely the very same thing every time it is called with the same arguments. It doesn't change its behavior based upon any external state. Moreover, these mathematically ideal functions not only are unaffected by the outside world except the input parameters passed to them, they also don't modify anything outside themselves. They don't produce any side effects, they only produce a return value. So, in other words, an ideal function doesn't read or write any mutable data which is outside of the function. If you watched the earlier video about programming languages, you may recognize that this is the ideal which the functional paradigm aims for. But this is just an ideal, and even in the functional paradigm, we never fully achieve this ideal. And this is simply because for programs to ever do anything useful, they have to interact with things outside themselves. They have to interact with state existing outside the program. And so we can't have a program consisting entirely of functions that deal only with data internal to themselves. What you should take to heart, however, is a general guideline to minimize shared mutable data. Shared here meaning data which is visible to different contexts, data which isn't just internal to one function, but rather seen between one or more functions. And also note that again, the concern really is with just mutable data, mutable state. Immutable data, immutable state, cannot be changed, and so it doesn't really matter if multiple contexts are using the same immutable data, because then what one context does with that data is never going to affect the use of that data by any other context. If we have something that's mutable, though, in one function, I might change a value, which then changes what happens when I invoke some other function. So the essential problem with shared mutable data is that it creates cross-dependencies. But one of the main purposes of decomposing our code into separate functions is that those functions ideally are standalone. They are units which can be understood in whole just by themselves. When our functions have side effects that may affect other functions, our functions are no longer isolated. They're no longer self-contained. So if shared mutable data is bad, how do we avoid creating it in our code? Well, the primary example of a shared piece of mutable data is a global variable. If you're lazy and use global variables where you really don't need them, you'll soon find yourself swamped in shared mutable state. Global variables, though, aren't the only place you can have shared mutable state. The fields of an object, for example, while not global to the entirety of the program, they do represent data which is shared between the methods of that class. And such shared state is problematic for all the same reasons, though, of course, in these cases, the variables are at least localized to the class. So whatever problems this shared state might cause, the potential for error is much more confined. However, at its worst, object-oriented programming not only fails to solve this problem of shared mutable state, it can actually enable it and merely disguise it to the programmer. A lot of programmers get it drilled into their head that the problem is merely global variables rather than just the general problem of shared mutable state. So they easily end up recklessly using fields as holders of shared mutable state, when what they really should have done is minimize their use of shared mutable state entirely. This is quite understandable though, because truly minimizing shared mutable state is often a quite difficult thing to do. Again, be clear, the goal is not to eliminate it entirely, because that's just not possible in most things we want to do in code. But each time you create more shared mutable state, you should consider very carefully whether it's truly necessary. Another very important consideration for keeping the complexity of your code under control is the structure of your dependencies. The general principle is that, ideally, dependencies should go in one direction. Or, to put it more accurately, the graph of the dependencies in your code should form what's called a directed acyclic graph, a DAG, a DAG. For example, this tree here is a directed acyclic graph, and understand that the arrows denote the direction of dependency. So here A depends upon B, and B in turn depends upon D and E. If we also had a dependency from E back to A, this would no longer be an acyclic graph, it would be cyclical, because the relationship between A, B, and E forms a cycle. Likewise, if we had a mutual dependency where B depended upon E, and E depended back on B, well, that's also a cycle. Now, the ideal dependency structures are those which form a neat tree, like what you see here. But if we throw in a cross-dependency, like here from B to C, well, now it's no longer a proper tree, but it is still a directed acyclic graph. Now, we need to explain two things. First, what exactly do we mean by a dependency? And second, what's so bad about cyclical dependencies? Well, a dependency is just a broad term for any time one piece of code relies upon some other. Usually we're talking about, say, functions which rely upon other functions, classes which rely upon other classes, or modules which rely upon other modules. So, for example, if in your code you bring in some library to use, well, your code depends upon that library, but the library does not in turn depend upon your code. The library is independent. You are referencing and invoking the code in the library, but the library is not doing the same with your code. Now, the general problem with dependencies is that the more dependencies a single component relies upon, the harder it is to understand and work with that component in isolation. Mutual dependencies are even worse in this regard, because then when two things depend upon each other, I can't do anything with one without consideration of the other. The ideal component has the independence of a library. It's something which is written almost no specific consideration of the code which is going to use it. It has a well-established public interface for how it should be used, but its internals are a black box known only to itself. So, the problem with cyclical dependencies is that they are mutual dependencies, and mutual dependencies can't live up to this black box ideal. Now, I should be very clear that eliminating all mutual dependencies from the entirety of your code is, in most cases, not totally feasible. Still, it's very important that you not be lazy and at least attempt to minimize your mutual dependencies. Otherwise, as your code gets larger and larger, it'll just get out of hand. It will get more and more complicated, and you'll start introducing bugs and have a harder time fixing your existing bugs, and a much harder time introducing new features. So we've said everything we'll say here about what good code looks like, but what about the actual process of writing code? Especially when I sit down with a new project, where do I even start? Well, in software development, there's actually a whole field of opinion about the process of writing code called methodology. There are many competing methodologies out there, kind of like how there's tons of contradictory dieting advice. A lot of the methodologies out there are very formal, and they have in mind software development conducted in large groups, such as in a big company. As long as you're still just learning to program, I recommend you stay away from those kinds of methodologies, because they tend to be, at best, just not very helpful or even insightful for someone working on their own, which is, I assume at least, how you'll be doing most of your coding for quite a while. Rather than go into the details of any popular methodology, I'm just going to give you a few broad themes found in a number of popular methodologies. First, when you start on a project, you have two basic different approaches. You can try working out your design from the top down or from the bottom up. Working top down means that you try and figure out what all the components are and how they relate to each other. In other words, it's working out the design on a macro level, whereas in a bottom up approach, you don't presume to figure out the broad strokes ahead of time. You just start in on something that you think you need and you actually try and implement that. You actually start in on writing the code for one or a few components and you just see where that leads. Now, the reality is that there are problems with both of these approaches. When you're working top-down on any non-trivial problem, you're painting in the broad strokes without account for the details, because, of course, even the smartest human mind is limited, and we just can't think of all the details, we can't predict them all. If we could, we wouldn't have to talk about methodologies, we'd just sit down and write all the code. So, what can happen is that you will work out a top-down design, and then you'll go to actually write your code, and you'll realize that, oh wait, the way this is all structured doesn't make sense once I get down into the details. It may turn out that this component and this component just don't really fit well together, and it may turn out that there's whole things that you've missed, that you've forgotten about, and so the whole macro structure may need to be rethought. Conversely, if you start with a bottom-up design, you're not even trying to anticipate a macro structure for your code. You're basically just letting the code accumulate as you write it, and so the macro structure that then emerges tends to be messy and complicated. The other danger is that if you just set in to write code without consideration of the whole of the project, very commonly you will end up having to reassess and realize that, oh, all this code I've written, it's not even what we really want anyway. Either it just doesn't fit properly and where the whole structure needs to go, or maybe it implements some feature that we don't even really need. So the practical reality is that we shouldn't use either a purely bottom-up approach or a top-down approach, but rather some mix of the two. But of course, thinking in terms of top-down versus bottom-up, those are directly contradictory. You can't do them at the same time, So really in practice what you do is you go in a cycle. You spend a bit of time thinking in terms of top-down, then you go bottom-up, and you go back and forth. In other words, it's an iterative process of reassessment. And you do this constantly, not just at the start of your project, but throughout the whole thing. This is basically the dominant common theme of all methodologies out there today. In an earlier time, like back in the 60s and 70s, people had a notion that you would do everything top-down, that you should have a definitive plan where everything is thought out ahead of time, such that the actual process of writing the code is just fulfilling a design, like it's just filling in an outline. With a few decades of experience, most people realized that, hey, that just doesn't work. If we can't figure out what all the details of a complicated system should be all at once and hold that all in our head, then we can't successfully predict what an outline of all the details should look like. Another very effective strategy is what's often called exploratory development. The idea is that when we set out to do a project, when we sketch out our first top-down design, there are some aspects which we're more comfortable with than others. There are components which are very like things we've already done before, and things which we've never done at all. It's these unfamiliar areas especially which are sources of uncertainty. We have very great difficulty making even preliminary plans in these areas because we really don't know what we're dealing with. So, say for example that you set out to write a game, yet in your prior experience, you as an individual, or perhaps those of the people you're also working with, maybe you've never created a game. Maybe you've never dealt with rendering two-dimensional graphics or three-dimensional graphics. Maybe you've never dealt with audio or basic AI routines. In such cases then, a very effective thing to do is try and explore those areas in isolation. Like say, maybe if you're comfortable with audio and 3D graphics but you know nothing about AI, you should concoct some very basic proof of concept project, something that allows you to focus on AI itself, even if what you write will be totally scrapped and won't be integrated into the larger project. You're really just trying to familiarize yourself with this domain. And in other cases, maybe you're working with some library or some framework you've never worked with, and you're pretty sure you want to use them in your project, but you're not really certain because you don't know exactly how it works. You just don't have any experience in this area. So again, it can be very useful to concoct some small project where you can use this library or framework in isolation just to get yourself comfortable with it. This can be very worthwhile, even if the code you write is going to get tossed out. Lastly, the principle common to both of these themes is that, just like in writing English, good writing is actually a process of rewriting. So you shouldn't paralyze yourself with the expectation that the first thing you're going to write down is going to be perfect, or even perhaps simply functional. It's just very, very rare to set something down in text and get it right the first time, or even the second, third, or fourth time. The corollary of this is that if you expect to write well, you should constantly reassess what you have already written. If you don't rethink what you're doing as you do it on a regular basis, what tends to happen with your code is that it gets more and more complicated and messier, and it becomes an albatross around your neck.